Hello, this is Samuel Anderson going through the cumulative video where I've combined the formulas. I've over here are the formulas we're using. I've written out several formulas, several definitions of what these variables are. And you see on left, I have a complete spreadsheet where there are some normal words under the description, and there are some bold descriptions and values. So interestingly, using the bold values, I am able to find every single other value shown in the formula, shown in the spreadsheet. So if you notice, the bold values have to do with rocket specifications and also the acceleration of gravity, which for some reason on Earth is kind of important, it affects everything, right? Negative 9.8 something meters per second squared. I have that as a constant, and I am treating this as a constant. However, and the reason for that is the height change of this rocket is not necessarily a lot, but keep in mind, the farther you are from Earth, the less the gravity is going to affect you because it's like some force the acceleration, no, the gravity is going to be like force, mass 1, mass 2 over radius squared. And the radius has to do with your distance from Earth, and that changes a lot. But that aside, I will move on from that, and we will try and fill out this spreadsheet on the right. There are several things to keep in mind when doing this. And importantly, I have a diagram, which will help make everything more clear conceptually. So just going through the values I have written out, I have time for the rocket fuel to empty, I have exhaust velocity, I have dry and wet rocket mass, and I also have gravity. Right? So 4 out of 5 of the bold values are actually rocket specs. So down here, I have a diagram of rocket flight with the y-axis being height only and the x-axis being time. Keep in mind that the x-axis is not also a distance. So even though a rocket usually does make a curve like this in 3D space, the x-axis is time. We're pretending for now that the rocket is going just straight up and straight down. So there are 4 points that are important in this rocket diagram. We have points A, B, C, and D. Point A is the farthest left on the time axis. So we're calling this time is 0, right? And the rocket actually has not started lifting off yet. From point A to B is where the rocket uses up all its fuel. And at point B, the rocket has lost all its fuel, and it's starting to just coast and be affected by gravity only. So from points A to B, gravity plus the rocket acceleration will be the overall acceleration, and the rocket should go up, right? So we want positive acceleration. From points B to C, oh, and the change in velocity of the rocket from point A to B is going to be delta V, which is found using Tsiolkovsky's formula. That the delta V will be equal to a velocity of 0 at A plus that delta V. That's going to be the final velocity at point B. From points B to C, where the rocket's going to be coasting, and from B to C to D, technically the rocket's only going to be affected by gravity. But from B to C, the velocity is still positive, and so the rocket is still going up and up and up. Point C, the velocity is 0. Same for point A, actually, the velocity is 0. I said that, but I did not write it. At point C, the velocity is 0. And over points B to C to D, the acceleration is going to be gravity. We'll just call that gravity, negative 9.80655, something like that. So velocity at A and C is 0. Acceleration at A to B is going to be the thrust, which we will find. The acceleration from B to C to D is gravity. And the velocity is positive from A to C and negative from C to D. There's a lot going on. Using the rocket specs, I will be able to find the total height, which will be displacement of A and B, and then B and C combined. And same for C to D, actually, but that'll be negative because it's a change. And we will also be able to find overall time that the rocket's in the air. So, given our values, we have time for rocket fuel to empty, wet, dry. Okay, I already went through that. Let's move on. Just get into the nice stuff. Let's see. For velocity A, I said there was a velocity of 0. Same for C. Have that written down already. Said the acceleration from B to D is going to be gravity. So this is going to be is equal to G. I already have some of these cells pre-labeled, and you see I typed in G, and that is because I clicked on this cell right here, K14. I went up to here, changed the name of it, and now I can factor it in to any equation and write it like something a human would read, right? Something more similar. From the acceleration from A to B, we don't know. The velocity A, we know. Let's see. What about the time from A to B? The time from A to B, I said, is when the rocket's actually lifting off, and it's exchanging that mass for velocity. So all the fuel goes down, the rocket goes up, and the net momentum is actually 0. That's how Tsiolkovsky's formula was derived. I did go through that in the other video. But anyway, the time from A to B is going to be 20 seconds, which we have. But I'm calling that time to empty. Time from B to C and C to D, we don't know. We don't know anything else. So anything that's not written down, we don't know. Oh, except initial total rocket mass. The overall rocket mass is going to be equal to dry, or like the whole, and the fuel combined. Let's see, wet mass. It's going to be one of these. Yep, there we go. Where is D mass? No. Let me just click on the cells. That'll be easier. So I'll click cell 1, cell 2, and you can see, you can sort of read it. These titles are not the best because I used better titles up here in like good programmer camel Ks, and I can't reuse those. But 1035 is our total rocket mass. So probably the best formula to use for right now is going to be delta V. We can use delta V to find other stuff. So the velocity of let's see, we have rocket specifications. That's really all we have to go off of. But we have velocity of the exhaust. We have the initial and final mass. Oh, and that's it. So taking this formula and plugging it into delta V, we said velocity B is going to be the velocity A plus the change in velocity up to that point. Velocity A is 0, so velocity B will just be delta V, and that'll be velocity of the exhaust. I do not know what I named it. V exhaust. That kind of makes sense for some reason. Let's see. Velocity B is equal to, and really that's assigning. That is not an equivalency or a Boolean. Is equal to not gravity. Exhaust velocity times the natural logarithm of the initial mass is going to be the dry and wet fuel combined, or 1,035 grams, because that's when the rocket has not used up all its fuel, over the final mass, which is just 35 grams. And here the specifications are something similar to a baking soda and vinegar bottle rocket. If you had an entire liter filled up, so I'm going off that, right? Soda bottle, 1 liter, is roughly 35 grams. And 1 liter has roughly a kilogram of vinegar. So, velocity of the exhaust, logarithm, yes, this should be good. We end up with 50.802, and that matches our previous spreadsheet. Keep in mind that our rocket specifications and gravity all have at least 5 sig figs. So our derived answers will all have at least 5 sig figs. I can do that. I'll skip that part for now. Let's see. We have velocity B. We do have time from A to B. Is there anything else? Displacement from A to B and acceleration from A to B. Acceleration is going to be found using this equivalency right here. Delta V is equal to AT. But we do not know time. So let's find that using our final and initial velocity, right? So displacement is equal to time over 2 times the final and initial velocity added together. So basically it's an average multiplied by the time of the velocity. Kind of makes sense. Let's see. Yeah, so this is just an average multiplied by time. So you end up with just meters in your units. So displacement from A to B, I'm just going to plug and chug that formula. Time A to B, we said divided by 2, but we will multiply by the velocity of the final. We said V velocity B plus velocity A. Velocity A is 0, so it's just velocity B we're worried about. We divide by 2. This should be 508.02 meters, 021 as our final answer. Looking good. Now we just need acceleration, and acceleration is going to be equal to delta V over T, change in velocity, net change in velocity over time. That will be the delta V, we said was same as velocity B, over time from A to B is 20 seconds. So our acceleration from A to B, this is wrong, isn't it? What did I do? We have delta V over time to empty, looking good. 15, 35, 20. And from here, we actually need to subtract gravity because gravity is always acting on the rocket, no matter whether it's thrusting upwards or not. We end up, we're supposed to add gravity actually. Because, yeah. So I think I messed that up in my previous spreadsheet. Supposed to add. That would do something. Yes. So technically we have a negative acceleration from A to B. So what this says already is that our rocket is actually not powerful enough with these current specifications to launch. So we would need to change something like exhaust velocity. Say instead of 15 meters per second is 80 meters per second. Now we have a positive acceleration. So it has to be much more powerful. Exhaust velocity. Let's make this 80 meters per second here as well, so our numbers match. So that's everything, all the information we want from point A to B. That's probably the hardest part, actually. Now, time from B to C. displacement from B to C and velocity C. We actually know the initial and final velocity from points in time from B to C. And acceleration. Let's see. Let's try any formula. We're looking for probably, we know velocities. Which formulas do we know velocities in? We have displacement is equal to time over 2 times this. Do we know displacement or time? We do not. We do, however, have this formula, V final minus V initial is equal to AT. Should we use that? The answer is yes. We can find, no, that's not true. I'm having a conniption fit right now. You have delta displacement. What did I find first? I will look at my, this is what the previous spreadsheet's for. Velocity C minus velocity B over gravity, time, delta V over gravity. Right, okay. No, never mind. We do know what acceleration is. So delta V is equal to AT will help us find time. Duh. We know what the acceleration is. That's gravity. So take delta V over acceleration is going to be equal to time from B to C. So we put that in. We said delta V is the same as velocity. No, delta V. It would be 0 meters per second, and this minus this. So we'd put is equal to velocity C minus velocity B. We divide that by acceleration of gravity, and we obtain 27.629 seconds. Right. We have time. We don't have displacement. We use the displacement with acceleration and velocity, or with time and velocities, because this is easier. Why not use that? We have time over 2. So let's take time from B to C, and divide by 2, multiply by final is velocity is going to be 0 point C minus velocity B, and we obtain a negative number, which is wrong, over VC minus VB. We are adding, excuse me, we're adding the velocities because this is an average velocity. That would do that. Now we have a better number. Now we have everything from B to C, and we're looking for time from C to D, displacement, and velocity. Velocity, however, is going to be the easiest to find because that's just a time followed by acceleration. We know acceleration. We do not know time. Is that true? Acceleration. We do not know what the final velocity is. So we have to take the top formula up above. Displacement is equal to acceleration, gravity, times time squared over 2, plus the initial velocity, which is 0. So this is just going to be d is equal to acceleration times time squared over 2. We obtain displacement is equal to, we do not know time. Tricky. What did I do over here? Velocity plus gravity, time to d, c to d. Velocity c. Excuse me, we know what displacement is. Displacement, I was working on velocity. However, we know what displacement from C to D is. That'll just be the addition of A to B and B to C, right? Your rocket starts here, it goes all the way up to the maximum height, and it must come down. What goes up must come down. So you end up with this number. It's just simple addition. That is why it's not on a formula, because it's just a simple conceptual mistake which I made. So we know displacement. We can use displacement to find not acceleration, but we can use it to find time based off the initial velocity. So we can take some formula, right? And from the time from C to D, I did the work previously and ended up with the square root of 2 times the distance over gravity. That will have to do with t being squared in the top formula. Let's see. We're looking for time, so we're looking for t. We know what distance is, we know what acceleration is, and we know what the initial velocity is. So we use this formula because there's only one unknown. And by doing some algebra, we isolate t squared on that side and obtain this. 36.27 seconds. Now for velocity d, we will use time c to d. We will use the fact that we will use, let's see, that the change in velocity is equal to acceleration times time. So our final velocity at point D is going to be equal to the change in velocity plus the initial velocity, which is going to be AT plus V naught, or acceleration times time plus the velocity at C, which is 0. So the final velocity is just going to be acceleration times time, and that will be gravity times time. We said time from C to D, it's 36 seconds, and we get negative 355. Is that proper? It matches. Looks good. Is that our last formula? Looks like it. So now we know the times at every point, the displacements at every point, all the velocities, like how hard is the rocket going to hit? Do we need to account for that if we're going to make the rocket tough enough to withstand certain crash? There's a lot these numbers give you to work with to improve your rocket. Say you want to know how long the rocket will be in the air. This is it. If you're sending up a sounding rocket to study the aurora and you want to collect atmospheric data, you actually need it up in the air for a certain amount of time near the peak. So the total time, I am now freeballing here, but go with me for a second. Total time, because this will be on the quiz, total time is going to be equal to all of these combined. And this is just a simple sum right here. So our total time is 84 seconds. Our maximum height, we know, of the rocket. To make it easy, we will call it the absolute value of displacement from C to D. Oh, I forgot a negative sign here. There we go. Because the displacement is from the top to the bottom, so the net change is negative. So the displacement is going to be the absolute value of one of these, the bottom to the top. And we obtain this, which technically the answer I had. Displacement, velocity. We know what our crashing velocity is going to be. Assuming the rocket goes up vertically, right? A lot could change. That will be equal to velocity d. Is equal to velocity d. And that is everything. Thank you for listening to this video, and have a good time with that quiz. See ya.